NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will learn a clean, general method to solve floor equations of the form: the floor of a times x plus the floor of b times x plus the floor of c times x plus the floor of d times x equals k. We'll step through the algorithm, build intuition visually, and then summarize the key condition. Step 1. We write x as n plus p, where n is the integer part and p is the fractional part between 0 inclusive and 1 exclusive. We'll illustrate this on a number line with a tick at n and a tick at n plus 1 and a highlighted segment of length p. Step 2. We express a times x, b times x, c times x, and d times x as integer parts plus fractional parts: an plus ap, bn plus bp, cn plus cp, and dn plus dp. Because p is between 0 and 1, ap ranges from 0 to a, but not including a. So the floor of ap can be any integer from 0 up to a minus 1. The same logic applies to the floor of bp, cp, and dp. Step 3. Substitute these into the original equation. We get the floor of an plus ap plus the floor of bn plus bp plus the floor of cn plus cp plus the floor of dn plus dp equals k. Since an, bn, cn, and dn are integers, the floor of an integer plus any real number equals that integer plus the floor of the real number. So each term becomes its integer part plus the floor of the fractional part. Step 4. Group the n terms together and the floor terms together. That gives n times a plus b plus c plus d, plus the sum of the four floors, equals k. Let s denote the sum of those four floors. Then we can solve for n as n equals k minus s, divided by a plus b plus c plus d. Step 5. Because each floor of AP, BP, CP, and DP ranges from 0 up to a minus 1, B minus 1, C minus 1, and D minus 1, the sum s ranges from 0 up to a plus b plus c plus d minus 4. Therefore, for n to be an integer, the numerator k minus s must be divisible by a plus b plus c plus d. So the key condition becomes: a plus b plus c plus d divides k minus s for some s between 0 and a plus b plus c plus d minus 4 inclusive. Quick intuition example. Suppose it equals 3, b equals 4, c equals 5, and d equals 2, and k equals 17. Then a plus b plus c plus d is 14, and the range for s is from 0 to 10. We need s so that k minus s is a multiple of 14. Since 17 modulo 14 is 3, s must be congruent to 3 modulo 14, and the only s in 0 through 10 that works is s equals 3. Then n equals 17 minus 3 over 14, which is 1. This illustrates how the divisibility filter narrows down, and immediately. Summary. 1. Write x as n plus p, with p between 0 inclusive and 1 exclusive. 2. Expand ax, bx, cx, and dx into integer parts plus fractional parts. 3. Use the floor of integer plus y equals integer plus floor, y to separate the integer n term. 4. Define s as the sum of the four floor fractional terms, and solve n equals k minus s over a plus b plus c plus d. 5. Use the range 0 to a plus b plus c plus d minus 4, and the divisibility condition that a plus b plus c plus d divides k minus s to find valid n values. That is the core engine for these bracket or floor equations. Final takeaway. Search s in the interval from 0 to a plus b plus c plus d minus 4, such that a plus b plus c plus d divides k minus s. Then compute n equals k minus s over a plus b plus c plus d, and reconstruct x equals n plus p with p between 0 and 1. In this lesson, we will solve the floor function equation by following a clean, step-by-step algorithm. Here is our problem. Floor of x plus floor of 3x plus floor of 5x plus floor of 7x equals 56. We'll write floor using left floor and right floor brackets on screen. Step 1. Let x equal n plus p, where n is the integer part and p is the fractional part with p between 0 inclusive and 1 exclusive. Using floor properties, floor of k times x equals k, n plus floor of kp. So the whole sum becomes 16n plus the quantity s of p, where s of p is floor of p plus floor of 3p plus floor of 5p plus floor of 7p. we will keep floor of p for structure, but remember it is 0 for 0 less than or equal to p less than 1. Step 2. From the original equation, we get 16n plus s of p equals 56. Therefore, n equals 56 minus s of p all over 16. Step 3. We bound s of p. Since p is in 0 to 1, floor of p is 0. Floor of 3p can be 0, 1, or 2. Floor of 5p can be 0, 1, 2, 3, or 4. And floor of 7p can be 0, 1, 2, 3, 4, 5, or 6. So the minimum s is 0, and the maximum s is 12. Step 4. Because n must be an integer, 56 minus s of p must be divisible by 16. That means s of p is congruent to 56 modulo 16, since 56 modulo 16 equals 8, and s ranges from 0 to 12. The only possible value is s of p equals 8. Step 5. Substitute s of p equals 8 into the formula for n. That gives n equals 48 divided by 16, which is 3. Step 6. The condition s of p equals 8 becomes floor of 3p plus floor of 5p plus floor of 7p equals 8, because floor of p equals 0 on 0 to 1. We will now find which values of p in 0 to 1 make that true, and then translate to x equals n plus p equals 3 plus p. To see where the sum of floors equals 8, we plot all fractional breakpoints for 0 to 1. We place a number line with each rational breakpoint for 3p, 5p, and 7p. Now, by checking the intervals, the only segment where the sum equals 8 is p from 3/5 to 2/3. We shade that interval and label it as a left closed, right open interval. We can verify with a sample value, say p equals 0.62. Then floor of 3p is 1, floor of 5p is 3, and floor of 7p is 4. The sum 1 plus 3 plus 4 equals 8, as required. Finally, since x equals 3 plus p, and p lies from 3/5 to 2/3, x lies from 3 plus 3/5 to 3 plus 2/3. That is, x in the interval 18/5 to 11/3 with the right endpoint excluded. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.